Jai Hind to all. My name is Divya Sharma and today's video lecture is on phase transmission formula, fields from oscillating dipoles, SNR, and antenna parameters, antenna temperature and antenna impedance. These are the fundamental parameters of antenna: radiation pattern, beam width, directivity and resolution, beam area, radiation intensity, gain, effective aperture area. Now today we will discuss this antenna temperature and antenna impedance. Before that, first we will discuss the antenna height. Now, effective height. An antenna in a receiving mode, whether it is in a form of wire, horn, aperture area, etc., is used to capture electromagnetic waves and to extract from them. Now, effective height is defined as ratio of the magnitude of the open circuit voltage developed at the terminals of antenna to the magnitude of the electric field strength in the direction of antenna polarization. Effective height is represented as HE. Now, effective height is in meters of an antenna is also another parameter related to effective aperture. Now, if we will multiply effective height by the electric field, this is your effective height HE, and if you multiply this with the electric field, then we will get here voltage which is induced in the antenna. Now, effective height may be defined as the ratio of the induced voltage to the induced field. So, from this equation, effective height is equal to what? V upon E. Effective height you can measure in meters. Now, we will discuss the relation in between effective height and aperture. Let it be, for an antenna, radiation resistance is represented by RR matched with its load. So, power delivered to the load is equal to what? 1 upon 4 V square upon radiation resistance. Now, in V is equal to what? V is equal to HE. So, put here the value of V and we will get here power which is delivered to the load, that is equal to what? V is equal to 1 upon 4 V square upon RR. So, put here the value of V, that is equal to HE. So, 1 upon 4 H square E square upon RR. This is radiation resistance. Now, if in terms of effective aperture from the same, effective aperture, the same power is given by P is equal to SAE. And you all know in the previous lecture as we have discussed that S is equal to what? S is equal to E square upon ZE into effective aperture. So, we can equate this these two equations, H square E square upon 4 RR is equal to what? That is equal to E square upon Z naught AE. So, E square cancel out. So, from this equation we can derive HE, that is equal to what? AE upon Z naught RR 4 RR. Now, HE is equal to what? Under root this. So, HE is equal to what? 2 under root RR AE upon Z naught. So, this is the effective height which is derived when we are equating these two equations. Now, another way of defining effective height, let us consider transmitting case and equate that effective height to the physical height, and physical height length, that is L, multiplied by the normalized average current. So, that is equal to what? In terms of I means physical height, HE is equal to 1 upon I naught integration 0 to HP. This is the physical height. Physical height is represented as HP. And in bracket, in integration IZ. So, we have to integrate IZ with respect to DZ, and integration limits are 0 to HP. Now, here HE is effective height, HP is physical height, and now when we will integrate this, then we will get is equal to I average upon I naught HP. So, I average is average current. So, HE is equal to I average upon I naught into physical height. If you want to measure effective height in terms of physical height, Now, Friis transmission formula. So, when you have two antennas, transmitting antenna and receiving antenna, so this is transmitter, this is receiver. When you are sending signal from transmitter to receiver, so your signal is in form of radiation. So, radiation here, you are considering here isotropic antenna. Now here you have to calculate, you have to derive this Friis transmission formula. Friis transmission relates the power received to the power transmitted between these two antennas, and distance between these two antennas is r. Now let us assume transmitting antenna. This transmitting antenna is initially isotropic. Isotropic means you are considering here case of ideal condition. If the input power at the terminal of the transmitting of effective aperture, that is represented as AET, and power at the transmitting side is PT, and power at the receiver side is represented by PR, and effective aperture at the transmitter side, that is AET, effective aperture at the receiver side, that is represented as AER. So assuming that the moment that assuming for the moment that the transmitting antenna is isotropic, power per unit area available at the receiver side, that is equal to what? SR is equal to PT upon 4 pi R square Weber per meter square, and distance between these two antennas are represented by R, and PT is represented power at the transmitter side. Now SR is equal to PT upon 4 pi R square Weber per meter square. Let us consider, and if the gain at the transmitter side is represented as GT, so power per unit area available at the receiver antenna, which is increased in proportion SR multiplied by GT, gain at the transmitting side. So SR is equal to what? PT upon 4 pi R square into GT. Okay. Now power collected by the lossless matched receiving antenna of effective aperture AE. So SR is multiplied by AE, means aperture area, effective aperture at the receiver side. So SR into AER is equal to what? PT upon 4 pi R square into GT into AER. So this is the power PR. Power is power at the receiver side. Power at the receiver side is equal to what? SR into AER, means SR, this is your PT upon 4 pi R square into GT into effective aperture at the receiver side. So you will get here received power received at the receiver side, that is equal to what? PT GT AER upon 4 pi R square Weber per meter square. Now gain of the transmitting antenna is calculated as GT is equal to, so when you are calculating gain at the receiver at the transmitter side, so that is equal to 4 pi AET upon lambda square. So let it be, this is your first equation, this is second. So put GT here in this equation, that is equal to what? 4 pi AET upon lambda square. So put this value GT in equation 1. So you will get here value PR upon PT. So when you will put his value here, you will get here PR upon PT, that is equal to AER, effective aperture at the receiver side, into AET, effective aperture at the transmitter side, upon R square into lambda square. So this is your Friis transmission formula. Okay. Now next is fields from oscillating dipole. Let it be, you are considering here a dipole. If and you have charges here, let it be, this is Q, this is Q. So equal charges in a uniform dipole means, let us consider here is a straight conductor where there are two endpoints and charges are there at the endpoints, that is represented as Q. Both charges are equal but are in opposite sign. Let it be, here is negative, here is positive. Now when your charges moving with a uniform velocity. When your charges are moving with a uniform velocity in a straight conductor, then it does not radiate. But if charges are back and forth, means moving in a oscillating form, then there is a radiation in a straight conductor, right? And let us consider first case, when electric field line or wave from which charges at the end of the dipole, means here when you have maximum radiation, current is equal to 0, means there is maximum oscillation, maximum acceleration or deceleration. So you can say here I is equal to 0, acceleration or deceleration is maximum here, and you have a maximum radiation when time is equal to t is equal to 0. Let us consider the second case, when t is equal to 1 by 8t. It means what? When this is your electric dipole, means, or you can say straight conductor, when you have two charges are in opposite sign, when they are moving to each other, means in this in opposite direction, positive sign is moving in this direction and negative sign is moving in this direction. So it means what? Your radiation in this electric dipole is like this. So, and direction of current, that is positive to negative. Now here I is equal to what? I is increasing. Okay. Now let us consider the another case. Let us consider t is equal to 3 by 8t, means whenever we are increasing the time, means time, whenever we are increasing the time, let it be changing the time, t is equal to 1 by 8t, t is equal to 3 by 8t, t is equal to 1 by 4t. Now maximum time is t is equal to 1 by 2t. So here when you are considering this case, t is equal to 1 by t, so I is 0 here. I is not 0. When you are considering the case of t is equal to 1 by 4t, so I is maximum here and oscillation is minimum here. It means what? Acceleration or deceleration is minimum here and I is maximum. It means what? It means your this field is detaching from this uniform straight field. Okay. So what is the conclusion of this oscillating field in the oscillating? When you have a straight conductor and you have charges at both the ends in opposite sign, then if you have then your radiation is maximum and I is equal to 0, means it means here oscillation is maximum. Now if your field is detaching from this uniform straight conductor, it means what? I is maximum here and oscillation is minimum, and your field is detaching when you are changing the time. Now next is signal to noise ratio. If there is a antenna temperature in the field, so noise is also there, because antenna temperature depends on signal to noise ratio. So first we will discuss signal to noise ratio. It means what? It defines the quality of a signal. So generally output of the network is not same as the input. It means what? It means some changes in the characteristic of the signal at the output side. If your signal is not same, let it be this is your transmitting signal, this is receiving signal. So if you are sending some signal, let it be this is X. So if it is not same X, it means what? It means if there is a change in X, then it means what? It means there is a noise at the output side. So how we can measure noise? SNR is the ratio of signal to noise. So SNR at the input side, that is represented as SI upon NI, and SNR at the output side, it means S0 upon N0. Now we have to find out noise figure. So noise figure is what? Ratio of the signal to noise ratio at the input to the signal to noise ratio at the output side. So figure of merit or noise figure is equal to SI upon NI. It means this is your, let it be this is your SNR at the input, this is your SNR at the output. So equation first divide by equation 2, then you will get here noise figure. Okay. Now antenna temperature. So antenna temperature also affects due to noise, means if there is antenna temperature in this signal in the antenna, then there is some noise in the antenna also. So every object with physical temperature above absolute 0 radiates energy. So amount of the energy radiates is usually represented by equivalent temperature, that is represented by T. Now TA is equal to what? TA is equal to integration 0 to 2 pi, next integration 0 to pi. Here in integration TB in form of with units theta and phi, and G is G in bracket theta comma phi. So this is area, this is temperature gain, and this is your area, beam area, that is represented as sin theta d phi upon integration 0 to 2 pi. 0 to pi means this is the integration of theta, this is the integration limits of phi. Here also these are the limits of theta and these are the limits of phi, and these are the limits of theta. So here TA is equal to what? TB G, area of the beam area, or you can say upon G and then the area. So TA is the antenna temperature, or you can say effective noise temperature of the antenna, radiation resistance K. Now G is what? Gain pattern of the antenna. Now assuming no losses are there, so between antenna and the means if you have antenna, transmitting antenna and receiving antenna, and no losses are there, then PR is equal to what? PR is equal to K TA delta F. PR is your antenna noise power, that is represented, its units are what? K is Boltzmann constant, TA is your antenna temperature in Kelvin, and delta F is bandwidth in Hertz. So when there is no loss, let us consider there are no losses in between when you have antenna, when power transferred from transmitter to receiver side, then your PR is equal to KTA delta F. Now next parameter is, and this is the last parameter of antenna, antenna impedance. Antenna impedance is the impedance at the point where the transmission line carrying RF energy from the transmitter is connected. So this impedance is known as antenna input impedance. So let us consider this is the circuit diagram. This is the source represented by VG, and this is at the receiver, means this is the receiver side, antenna receiver side, and between source and antenna receiver side, this is transmitter, this is receiver. So this is the transmission line. Here are standing waves are there. So at the source side, your impedance is represented by ZZ. So it is antenna temperature is what? Antenna temperature is the quantity which is opposing current in a circuit diagram, right? If we apply voltage in the circuit, then it means what? Current is produced, right? Resistance plus reactance means what? This is real part, and reactance means what? Imaginary part. So ZG is the combination of real plus imaginary. Okay. Now resistances are the receiver side, means at the antenna you have loss resistance. Now RR is radiation resistance. This is the impedance XA. So let us consider this is whole is ZA. So ZA is equal to what? This is the real part of the resistance, and this includes the real part as well as imaginary part. Now ZA is equal to what? ZA is the ratio of VI upon II. ZA is a complex quantity. Complex quantity means what? This is the real part and this is the imaginary part. Now ZA is represented as RA plus JXA, and RA is what? Let us consider you have real parts RL, RR. So these are real parts. So if you want to find out impedance of these resistances, so RL plus RR are real part, and JXA, this is the imaginary part if it is there in this resistance, right? Now RA is equal to what? RA is the reactive part. Reactive part means loss resistance plus radiation resistance. So RL is represented as loss resistance, and this is radiation resistance. So combination of loss resistance and radiation resistance, this is real part, and this is a combination of real as well as imaginary part. So impedance is what? Impedance is equal to VI upon II. Okay. And ZA is what? ZA is a combination of real and imaginary part. Okay. So this is the antenna impedance. So this is the last parameter of antenna. Now this unit is completed. Thanks, and next topic we will cover in the next video lecture. Thank you.